Hello everybody, this is Jim Corkins and welcome to the last part of our forces module in your physics course. If you haven't done the reading, please do so. Now this is 4.5 force diagrams on an inclined plane. So up until now we've been studying how our coordinate system is completely up and down and left and right. Okay? Where positive x direction is to the right, negative x direction is to the left, positive y direction is up, negative y direction is down, and really in the third dimension, positive z is out and negative z is in. However, there are some uses to turning that coordinate system such that the positive direction can be up the plane if it's twisted. That would be counterclockwise, or if you twist it clockwise, the positive x direction will be down the plane. Okay, so there are uses for that, and the primary use that we want to use it for is to keep the horizontal coordinate system parallel to the plane of motion, which would then in turn make the y direction part of the coordinate system perpendicular to the inclined plane. Okay, so there's a little bit of nuance to this, but I could show you how to make those, how to twist the coordinate system, well, when to twist it, how to twist the coordinate system, and then what to do after you twist that coordinate system. Okay, all right. Now, let's go ahead and let's actually do an example. The best way to learn this is just to do an example. Okay, so for example, if you had a box being pushed up an inclined plane with a force F, and that box is 2 kilograms, and it is a rough inclined plane, and the inclined plane is at 30 degrees. So this would be 30 degrees right here. Now, before we get into the force diagram and twisting the coordinate system, typically these problems do give you an inclined plane, and I'm going to do this over here. They give you a picture to go with it. If they don't, draw the inclined plane and draw it as such, and we're going to have the inclined plane pointing up and to the right. The angle is 30 degrees. Okay. Now, again, what we do is put our dot at the center. I'm doing this off to the side to show you how to construct this. Okay. And so what you want to do is you want to draw it such that the coordinate system, the x direction coordinate system, draw that one first, goes through the dot, put the dot at the center here, and make sure you label your coordinate system. Positive x, negative x. And then you want to make the y direction coordinate system perpendicular to the plane of motion. Okay, so we're going to call this negative y and positive x. So in a way, our coordinate, our x direction system right here, our normal coordinate system, can't draw and talk at the same time. We had to twist it counterclockwise so that the x direction is parallel to that plane that we that inclined plane that we first drew. Okay, so that's how we got this inclined plane. All right, now going over here, and I am going to be going back and forth in between these two things to show you some things. What we're going to do is we're going to start off doing our force diagram like we normally do. Okay, so the first thing that we're going to do, like we do in all force diagrams, after you've drawn the coordinate system, we're going to draw our mg vector. And we always want our mg vector pointing straight down towards the bottom of the plane. Now, our mass is 2 kilograms. Okay, so that is 2 kilograms times 10 meters per second. So this would be 200 newtons. and that is our mg vector. Notice I did not label that negative or positive. Because this vector is not aligned to our coordinate system, we don't know if it's positive or negative, okay? Once we align the components of this vector to our coordinate system, then we could label it positive and negative. For example, if we had a vector pointing up and to the left here, that vector would have a negative x components, but also positive y components. So it's kind of hard to say. And if it was pointed over here, kind of to the right there, it would have negative y components and positive x components. So any diagonals that are not aligned to your coordinate system, just like in our trig review we did in a while ago, they cannot be aligned to our coordinates. They are not positive or negative until they are aligned to the coordinate system. Okay. Now, now we're going to draw the rest of our vectors. Okay, so once we have our non-contact force out of the way, now we just have to ask, what is physically touching the object? Well, it said the force was pushing the object up the plane of motion, so at a constant velocity. So that force, we're going to label it F. And I don't like turning my head too much. But that is pointing in the positive x direction. I suppose I should make an effort to turn that thing. So it's pointing in the positive positive x direction. Okay. Okay. Now, the only other thing physically touching the object is the surface. Okay. Now, the surface is going to have two components, like we have learned. It's going to be pointing, first of all, the surface has to hold the object up, so that's going to be the normal force, pointing in the positive y direction. And since the object is moving up and to the right, this has got to be pointing opposite that direction. So friction is pointing opposite that direction, which is going to be negative u sub k times the normal force, which is going to be negative 0.25 times the normal force. Let me write it right here. Negative 0.25 times the normal force. And that is our negative mu sub k, kinetic friction, since it has a velocity, times the normal force. Okay. So that is our force diagram. Now, normally when you have a vector, in this case our mg vector, that is not aligned to the coordinate system, it's pretty easy to tell what angle it is. And the problem is right here, our angle, 30 degrees, is right there. So how are we going to align this downward pointed vector using this 30 degrees? Okay. Now, what I'm going to do is I'm going to prove this to you, but I'm just going to say that angle right here is this angle right here. So this is our 30-degree angle. And I'll show you how I got that using our drawing over here. So I'm going to draw our mg vector pointing straight down. Okay. And what I'm going to do is I'm going to continue that line straight up. Okay. Now, we know if this is 30 degrees and this is 90 degrees, then this is going to be 90 minus 30 degrees, which is 60 degrees. So that means this is also 60 degrees, right? So this is also 60 degrees. However, this whole area right here, that composes 90 degrees. The y direction coordinate system is perpendicular to the x direction. So if that part, if this whole thing from here, this arc right here, and let me do this so that it makes sense. So this is our 90-degree angle. Let's use blue for this. So this is our 90-degree angle. Okay. And so really, since this whole angle is 90 degrees, this part is 60 degrees. That means this part right here, and I'll use purple, this has got to be 30 degrees, because 30 degrees plus 60 degrees is equal to 90 degrees. Okay? So that's how this is 30 degrees. Now, that been stated right there, my brain does not go, oh, this is 30 degrees, this is then got to be 60 degrees, and this is then got to be 30 degrees. It's more of a pattern recognition. I see this is 30 degrees, so that this angle, the angle in between the y component of the coordinate system and mg is 30 degrees. Okay, so that's what I do. I don't do this in my head at all. Not until I'm asked to do it, and then I justify it to you guys. Okay? Okay, so the last thing that we have to do is we have to then break up this diagonal vector, the mg vector, into up and down and left and right. Now to do that, what I think of is this. I think of the x direction coordinate system. So to help me recognize the triangle, and to break up this mg diagonal into and recognize that that's a hypotenuse, what I do is I let this x direction horizontal axis sink down until it meets the tip of this. So what I typically see is I see students, here's what I mean. This is a diagonal, and any diagonals are the hypotenuse. But what I see students do a lot is do this. And so now I have not aligned this hypotenuse to the coordinate system, and that is because I've made that a side. But now I've created another vector that is not aligned to the coordinate system. So I've just made the situation worse. And what I want to teach you to do is to recognize that it should look like this. And this will be our triangle. And that is our hypotenuse. So if you tilt your head a little bit to the left so that your top of your head is pointing this way and bottom of your chin is pointing down that way, you can see that that's a hypotenuse. So I want to teach you to recognize that this is the triangle. And how I think of it is I think of this x direction coordinate system sinking down, right? So I'm going to draw it, and I'm going to draw it such that starting at this tip, I'm going to sinking down so that when it's a straight line, and when it sinks down all the way down this y direction vector here, that when it meets the tip of this, it's easier now to recognize that as the coordinate system, where this is still negative y, and this is still positive x. So you got to keep the current directions on that coordinate system. But now it's easy to recognize that that is a hypotenuse, and here are the two sides of our coordinate system. And so once you do that, you can see, well, here is our triangle. And these are the two sides, where one side is the mg vector, which is 200 newtons, and this side, and this is the other side. And so when you twist your head, you can see that it's pointing down and to the left. So that means the vertical part has to be pointing in the negative y direction. The horizontal part has to be pointing in the negative x direction. The side that is cosine is physically touching the 30 degrees. So this is going to be mg cosine of 30 degrees. And I should have put a negative in front. So that's pointing in the negative y direction. So that's mg cosine of 30 degrees. In other words, that's negative 200 newtons cosine of 30 degrees. If that's cosine, this has to be sine. So this is going to be and it's pointing, this vector is pointing in the negative x direction, so that's negative mg sine of 30 degrees, which is negative 200 newtons sine of 30 degrees. Okay? It does take a little bit of practice, but after a little bit, you'll be able to recognize if that's 30 degrees and you've draw your force diagram first, and then you'll see, and then this has to be 30 degrees. So if this is 30 degrees, that 30 degrees has to be in between the y coordinate, the y direction of the coordinate system, and mg. And to recognize this is your triangle, I let the x direction part of the coordinate system sink down. So I'm imagining this x direction just floating, sinking down, and when it meets the part of it touches the tip of that, that is our x direction part of our coordinate system, and that helps me recognize this is our triangle, and that is the hypotenuse. Okay. Okay, moving right along. In this problem, it says that this is moving up and to the right, so it's a positive x direction. Its acceleration in the x direction is 0. Its velocity in the y direction is 0. So that is 0, and its acceleration in the y direction is 0. Okay. Now, let's translate all of this stuff, and I'm going to use the numbers for the weight onto our x direction and y direction. So in our x direction, we have our negative 200 newtons sine of 30 degrees, our weight vector sine of 30 degrees. We have our friction vector negative 0.25 times the normal force. And then we have our F vector, right? So we have 1, 2, 3 vectors. And now we're going to set this equal to the 2 kilograms, and I looked here for this, times the acceleration in the x direction, which is going to be 0 meters per second squared. Okay. In the y direction, I have negative 200 cosine of 30 degrees. And then I have the normal force. And that is also equal to 2 kilograms times the acceleration in the y direction. Okay. So we could recognize pretty easily that the normal force, this is 0, so you're going to add the 200 cosine of 30 degrees onto the other side. 200 newtons cosine of 30 degrees, which is 0.866, so about 80% of 200, 173.2. So we know the normal force is going to be equal to 173.2 newtons. All right. Now, I'm going to copy this exactly as it appears here. So that's going to be negative 200 newtons sine of 30 degrees minus 0.25 times normal force plus F, and that's going to just be equal to 0, right? Now we're going to plug this right into here. 200 sine of 30 degrees. Sine of 30 degrees is a half. So this is 0.5. Just like this was 0.866. We're going to do the same problem again, but this time we're going to align the inclined plane is the other direction. And so I just want to correct some errors on this. This is pointed in the negative x direction, and that is 0, and that is 0. Okay, so, okay, cool. Well, if you're given this as your drawing, you have to twist your coordinate system so that the x direction is aligned to that surface, and the y direction is perpendicular to the x direction. This is the same problem, so that this is our 30-degree angle, and this is our 2-kilogram object. And again, it's being pushed up the plane of motion with some force F at a constant velocity. Okay? Now, in this case, our mg vector is going to be pointing straight down, again, towards the bottom of the page. And we know that is 200 newtons of force. Okay? Now, I want you to try thinking about this for a second. And remember the rules. If this is 30 degrees here, how do you recognize where the 30 degrees is relative to the mg vector? Okay? Well, that 30 degrees, again, has to be in between the y direction of the coordinate system and that mg vector right there. So that's our 30 degrees. Okay? Once we have that aligned, now you can take a moment and break this up into up and down and left and right. I prefer to finish the force diagram and then break up the diagonal vectors. So that's what I'm going to do. Well, the two things touching this is the force pushing it up the plane of motion. So that is pointing, that is really, that force is pointing that direction. And that is going to be, in this case, it's going to be a negative F. Okay? And we have the surface force, which we have the normal force. Oops. You know what? I'm just going to, this is our normal force. It's pointing in the positive y direction. And since the velocity vector is up the plane, our friction vector, our kinetic friction vector, has to be pointing down the plane, opposite its direction. So that's going to be a positive 0.25 times the normal force. So that's our friction vector. You know what? I'm going to write that right here. Positive 0.25 times the normal force. Yeah. Let's try to, this is going to be hard. 0.25 times the normal force. That looks better. There we go. So that's our friction vector. Now, once we've done that, again, it's hard for me to recognize, I don't know about you, but this is hard for me to recognize that this is a hypotenuse. Again, I don't want to do this. If you do this, you've made a mistake, okay? Because now you have not only one vector that is not aligned to your coordinate system, now you have a second one. And so the trick is, again, which helps me, is seeing that that x direction thing, different stages, if it's sinking down, so it's, let's take that x direction, it's sinking down here, sinking down even further, and then it's going to sink down till it meets that. Okay? And so here is our x direction coordinate system, where this is positive x, and this is negative x. Yep. And so now, you can see this is our triangle we're working with. We want to make our triangle encapsulate that 30 degrees. And we want to make it so that that mg vector is we could see now it's pretty easy to recognize that that is the hypotenuse. And recognizing that, if you twist your head clockwise a little bit, you can see that that is pointing down and this is pointing to the right. So now this is going to be a negative 200 newtons, our weight vector, cosine of 30 degrees. And this is pointing to the right, so that's going to be a positive 200 newtons, sine of 30 degrees. Okay? And then from here, we've seen it before, just like we did before. We're going to go ahead and we're going to take our x direction vectors, which we have 1, 2, 3. So I see a negative f. I see a positive 200 newtons, sine of 30 degrees, and I see our positive 0.25 times the normal force, which this is going to be equal to 2 kilograms times 0 meters per second squared. That's the acceleration. In the y direction, I have 1, 2 vectors. So I have our negative 200 newtons, sine of 30 degrees. Actually, that should be cosine of 30 degrees. Can't have two sines. That's weird. And the normal force is right here. And then you set it equal to, you apply Newton's second law, which is going to be the weight of the object, or the mass of the object, times the acceleration in the y direction, which is 0. So again, this normal force, that is going to end up being equal to, what is it, 173.2. So this whole thing is negative 173.2 newtons. So the normal force is just going to be 173.2 newtons. We're cutting some steps. And then here you got negative F. This is 0.5 and this is 0.866. So this is going to be 200 newtons times a half, which is going to be positive 100 newtons. And this is going to be plus 0.25 times the normal force, so times 173.2 newtons. I am skipping steps because we already know what the answer is supposed to be, which is going to be equal to 0. So now we got 100 newtons plus what is that? I forgot. What is that? 173.5. What is it? 43.3. 43.3. So this is 43.3 newtons, and we're adding the F onto the other side. So then that weight force, so the force pushing it up is going to be hold on a second. Just want to double check. 173.2 times 0.25. Of course, I don't believe believe it. So this is going to be 43.3. So this is going to be 143.3 newtons, and that's equal to F. Okay, so I'm going to write that in up here. So this is 140. Oops. Just use black ink there. 143.3. Okay. Again, what we did, steps. We were given the picture here, so we lightly drew that inclined plane. We labeled our angle 30 degrees. Drew our center of mass. Wrote 2 kilograms. Wrote our coordinate system that was now twisted, such that the x direction is parallel to the plane of motion. The y direction is perpendicular to it. Then we started our force diagram by drawing our mg vector pointing straight down to the bottom of the page. Then this 30-degree angle makes the 30-degree incline is 30 degrees here in between the mg vector and the y direction of the coordinate system. And then we drew our contact forces F and the surface, which was those two forces. And then we broke up our mg vector to align it to the coordinate system by and so to recognize that that mg vector was a hypotenuse and this is our triangle, I let the coordinate x direction part of the coordinate system sink down till it met the tip of the mg vector. And then I wrote those two vectors. mg cosine of theta is touching the 30 degrees. mg sine of theta is opposite that angle 30 degrees. And then we started constructing our equations. Since there was friction present, we solved for the normal force first, and then we plugged in that normal force for the part of friction right there, and then did our algebra and solved for F. Okay, so that's the basics of creating force diagrams for objects that are on an inclined plane. Okay, the other ones, the only more difficult that you add, the only way to add it, more nuance to it, is just extra forces. So, anyways, I hope you enjoyed this. Thank you very much.